August 1943. Occupied France. Just before dawn, on a quiet Luftwaffe airfield hidden from public view, a single American fighter sat surrounded by German guards. It hadn't been reduced to twisted wreckage or burned into scrap. It had landed under control. The pilot was already in captivity. The aircraft itself was almost intact. To German command, this should have been a victory, a rare opportunity to examine an enemy machine up close. But for one man standing beside it, this aircraft would become something else entirely. Not a tactical puzzle, but a warning written in aluminum and steel. At first glance, the fighter looked wrong. Too large, too bulky. Its proportions offended every instinct German pilots had developed. It lacked elegance. It lacked grace. Compared to Germany's lean, aggressive fighters, it seemed grotesque. Luftwaffe pilots had already given it mocking nicknames, joking that it looked like a flying milk bottle. Sitting on the tarmac, it appeared absurdly overweight, as if it had no business ever leaving the ground. Many officers dismissed it instantly. American excess, crude engineering, a brute force design that sacrificed finesse for size. But the man examining it didn't care how it looked. He wasn't a combat pilot or a tactician shaped by dogfights. He was an aeronautical engineer, trained to trust numbers, materials, and physical limits. Before the war, he had worked in aircraft design, learning what could and could not be built under real industrial conditions. His job now was to identify weaknesses, assess threats, and recommend countermeasures. As he walked around the fighter, he ignored the jokes and focused on weight, structure, and layout. And the numbers immediately unsettled him. Fully loaded, the aircraft weighed nearly 8 tons. Germany's frontline fighters weighed roughly half that. This wasn't just heavier. It represented a completely different philosophy. German aircraft were built on the edge of possibility, shaving weight wherever possible to extract performance from limited engine power. This American fighter did the opposite. It accepted weight freely, almost casually. And that raised an uncomfortable question. What kind of engine could lift this much mass and still fight effectively? When the engine cowling was removed, the answer became impossible to ignore. Inside sat an enormous radial engine, 18 cylinders arranged in 2 rows, built with a level of precision that stunned everyone present. The sheer size explained the aircraft's bulky shape, but size alone wasn't what caught the engineer's attention. It was the finish, the uniform machining, the consistency, the materials. Every component showed time, care, and resources. This wasn't an engine built under desperation. It was built properly. As the engineer began calculating output based on displacement and configuration, the numbers pointed to something deeply troubling. This engine was producing at least 2,000 horsepower, possibly more under combat conditions. Germany's best engines were already stretched to reach 1,700, and even then they were fragile when pushed. This American engine wasn't fragile. It appeared comfortable at this level of power, as if it had been designed with margin to spare rather than pushed to its limits. What disturbed him even more was what he didn't see. There were no signs of material substitution, no simplified components, no rough finishes indicating rushed production. German factories were already being forced to compromise, using lower-grade alloys, reducing tolerances, and accepting defects just to keep aircraft rolling out. This engine showed none of that. It was built the way engineers wanted to build machines before shortages dictated otherwise. Then came a detail that revealed how differently the Americans thought. Each cylinder was individually removable. Damage didn't mean scrapping the engine or performing a full teardown. It meant replacing a part and returning the aircraft to service quickly. German engines required long, careful disassembly for similar repairs. This American design assumed damage was inevitable and planned for rapid recovery. That assumption alone spoke volumes about confidence and resources. But the engine itself wasn't the most terrifying discovery. As the engineer traced the ducting running through the fuselage, he realized what truly set this fighter apart. A turbo-supercharger system, fully integrated, not experimental, not theoretical. Exhaust gases were routed through heat-resistant channels to a turbine mounted far behind the engine, spinning at incredible speeds and forcing compressed air back into the cylinders. This allowed the engine to maintain full power at high altitude, where German fighters struggled to breathe. German engineers understood the theory behind turbo systems. They had experimented with them for years. But the materials, precision, and manufacturing complexity required had always defeated them. Bearings failed. Ducting cracked. Tolerances couldn't be maintained. And yet here it was, installed in a frontline fighter that was being mass-produced by the hundreds. Not a prototype. Not a testbed. A standard production aircraft. The implications were devastating. At the altitudes where bomber interceptions occurred, German fighters lost power rapidly. Mechanical superchargers simply couldn't compensate for thin air. This American fighter, by contrast, reached its peak performance there. Where German pilots struggled, this aircraft thrived. When asked whether Germany could replicate such a system, the engineer didn't hesitate. Not with current manufacturing capacity. Not while already failing to meet basic production targets. The conclusion was unavoidable. This wasn't just superior engineering. It was superior industry. The examination continued, and the story grew worse. The airframe itself told a tale of deliberate overbuilding. The aircraft had absorbed significant combat damage and still returned safely. Cannon hits that would normally tear a German fighter apart had been endured. The skin was thicker. The internal structure was heavier. Control systems were redundant. Armor protected the pilot from multiple angles. Even the windscreen was far thicker than anything Germany fielded. Most importantly, the radial engine acted as a shield. German fighters relied on liquid-cooled engines, where a single puncture could cause catastrophic failure. This engine had no vulnerable coolant system. Cylinders could be destroyed and the engine would continue running. Reports from Luftwaffe pilots suddenly made sense. They weren't exaggerating. They were witnessing a machine designed to survive punishment rather than avoid it. One engineer remarked that the aircraft was overbuilt, carrying weight that could have been traded for agility. The chief engineer agreed, but added something far more damning. The Americans could afford that weight. They had engines powerful enough to carry it. Germany did not. German designs were optimized because they had no other choice. American designs were forgiving because power and materials were abundant. Then the weapons were examined. 8 heavy machine guns mounted in the wings, each with a massive ammunition supply. The total volume of fire was staggering. A brief burst unleashed a storm of metal that overwhelmed anything in front of it. German fighters carried fewer guns, less ammunition, and relied on short engagements. This American fighter could stay in combat far longer. Accuracy mattered less when sheer volume achieved the same result. As the engineer compiled his findings, the pattern became unmistakable. Every component reflected the same truth. Advanced metallurgy, precision machining, complex systems, heavy construction, massive production. Any one of these strained German industry. This aircraft combined all of them, and thousands more were already on the way. Production figures confirmed his fears. Hundreds of these fighters were being produced every month. The engine powering them was also used in multiple aircraft types. Total engine production alone exceeded what Germany could hope to match across all designs. American aircraft output dwarfed German production by a ratio that could never be closed. And American aircraft were heavier, more complex, and built to higher standards. Writing the report was dangerous. The conclusions were blunt and deeply unwelcome. Germany could not win an industrial war against the United States. Continued losses against an enemy with superior numbers, materials, and manufacturing depth would lead to collapse. His superiors warned him. This would not be received kindly. But the report was accurate, and accuracy was his duty. The response was silence. Then dismissal. The report was labeled overly pessimistic, influenced by enemy propaganda. Reality conflicted with ideology, so reality was ignored. But events followed mathematics, not belief. American fighters appeared in greater numbers. Losses mounted. Experienced pilots vanished faster than replacements could be trained. Tactical adjustments came too late. After the war, the numbers became public. Over 300,000 American aircraft produced. Less than a third of that by Germany. Over 15,000 of these fighters alone. The engine that stunned the engineer was produced in quantities Germany could never approach, by factories that once built cars and trucks. When asked later whether he truly concluded defeat from examining a single aircraft, the engineer answered calmly. It wasn't the aircraft. It was what the aircraft represented. An industrial capacity so vast that tactics, courage, and ideology could never overcome it. Germany wasn't defeated by a single battle or a single mistake. It was defeated by factories it couldn't match and resources it didn't possess. And on that quiet airfield in 1943, standing beside one captured fighter, that truth was already impossible to ignore.